whatever. But all right, so here's the calendar. I've started the recording. So we are, I'm assuming everybody can hear me okay? All right, perfect. Okay, so we are here tonight, sequences and sums and set theory. So we'll see how far we get. We'll definitely get through sequences and sums and partially into set theory. So tutorial 2 was given last week, and that is due tonight at 1 minute to midnight. And tutorial 3 is up and ready. It's on sequences and sums, so the stuff that you learn tonight will you'll be able to apply to the tutorial. And in addition, there's of course the tutorial video that you can watch. And the assignment, of course, is due this weekend, and then next week is the quiz. So it's a little bit busy, but then the week after that, so this is the version of the calendar that we're going to go with. The week after that, we'll take a week off. Since we have so many weeks, we have a couple extra, so we can take that week off, and you guys can enjoy Canada Day. Hopefully there's will be some things open, and or what have you, or however you want to celebrate. Okay. About the quiz, I think I mentioned it. It's going to be the same as the other quizzes, but a little bit different in that it's not multiple choice or short answer. It'll be essay style, but there will be, so you can type out your answer in the space given. I'll give you a sheet full of translations that you can use instead of digging for the mathematical symbols. Although you can use the mathematical symbols, but I do find the CU Learn, you can use them, but I find it a bit of a pain and it doesn't always do what I want it to do. So the other option, and if you're going to do this, I would practice to make sure that you can get it working, is that you can write your answers down on a piece of paper or use a stylus or something, and then take a picture of it with your phone or whatever you have that you can use for a scanner. And then upload it. So there'll be an upload available. It's up to you to make sure that it's whatever picture you take is clear, that the TAs can understand it, and please write neatly, of course. So you can do that. And I'll give you probably, so there'll be 60 minutes, and I'll probably give an extra 10 or 15 minutes in order to handle any possible technical, the technical side of things where you do have to upload it and stuff. And so I think this Wednesday here, I should have the practice quiz ready. And that'll have a lot more detail, and you'll understand what kind of questions you'll be asked. And so you can properly prepare. And then, of course, as soon as assignment 2, the deadline passes, then I'll put up the answers for that as well. So you can use that to study from. It's mostly proofs. Do we have any midterms for this course? So no, there's no midterms. There's only 4. There's 4 quizzes. So we try and break it up, especially for a first-year class, into 4 smaller 4 quizzes that are worth less marks, just so that if there's a lot you're dealing with a lot as first-year students. There is an exam at the end, yes. And the exam is, by that time, we hope that you are good students and you can handle a final exam, because it is worth I'd have to take a look. I think it's worth 40 or 50. There are practice exams, yes. So there are practice questions for the final exam, and it's not, so the final exam is multiple choice, and the practice questions are not exactly the same, but if you can do the practice questions, then you should have no trouble on the final. Yeah. All right, bonus question. Yes, the bonus question. Yeah, so that won't show up right away because CU Learn doesn't handle bonus questions, but when I do your marks at the end of the semester, I put everything in an Excel sheet, and then I can, there's a mock exam on this Learning Center. A mock final, or it's possible maybe I unlocked it by accident. I mean, there's a practice quiz for quiz 1, some kind of mock exam. Okay, well, yeah, it's probably fine, whatever it is. So there was a practice for quiz 1. The practice for quiz 2 should not be visible yet because I have to decide on the final question. So I know the first 2 questions, but there's going to be a third question that is still a little bit up in the air. But yeah, it'll all be proofs, and so yeah. Anyway, just if you do the practice quiz and you know, look at the answers for the assignment and go through where you went wrong, then you'll have no problem with this quiz. Okay. Any other questions? All right. So let's get to, so I promised you last class that I would do some induction practice, some more practice with induction. So I have a couple examples ready to go. And then after that, we'll get into the main lecture. So let's do induction. Okay. All right, so prove by induction that 3 to the power n is less than n factorial for n greater than or equal to 7. So this actually ties into stuff that we're going to take later in the course. But for now, does everybody know what these terms mean? Well, actually, let's do a quick review just in case. So 3 to the n is 3 times 3 times 3 times 3, and that is n times. And n factorial, so that's 3 to the power n. And n factorial is equal to 1 times 2 times, whoops, times 4 times n. Okay, so these are both sort of fast-growing functions, but the n factorial grows faster, and we're going to prove it by induction. Okay, so every inductive proof, we have our 2 main steps. We have our basis step, so we have to prove it for a simple case, the base case. So in this case, that's 3 to the 7. So we want to prove it for n equal to 7, since that is the lowest number that we're going to deal with. And that's equal to 2,187, which is less than 5,040, which is equal to 7 factorial. Okay, so for n equal to 7, we have 3 to the power 7 is less than 7 factorial. And so that's true. Define integers and other number types on our assignments proofs. I think if it says you do, then do whatever is defined in the question, just use that. Generally speaking, I don't remember the exact questions. If you have a specific question number in mind, I can answer that. But generally speaking, the level of detail in the question is perfectly fine for your answer. Okay. Any other questions? All right. So now our inductive step. And our inductive step always sort of takes the same form. That is, we want to take whatever our proposition is or predicate is for k, and we want to assume that it's true for k, and then we want to prove that it's true for k plus 1. So in this case, I'm running out of space already. In this case, P of k is the idea that 3 to the k is less than k factorial, and that is our assumption. So that's our first fact, that we assume the antecedent is true, and we use it to try and prove the consequent. So how do we do that? Well, generally speaking, we want to take this thing that we've assumed is true and transform it into this thing. So we want to transform it into specifically p of the k plus 1 is there we go. 3k plus 1 is less than k plus 1 factorial. All right. Okay. So the first step we're going to do is we're going to do a little bit of math. So we're going to multiply both sides by 3, and that'll maintain the inequality. So this is true by math. And we multiply by 3, both sides. And then we can observe that, well, 3 to the k plus 1 is equal to 3 times 3 to the k, right? Which is less than 3 times k factorial, which is less than k plus 1 times k factorial, since we're assuming that k must be greater than or equal to 7. So that's math. We'll say that 7 is greater than 3. And then, so that implies that 3 to the k plus 1 is less than k plus 1 k factorial, which is equal to k plus 1 factorial. All right. So we've taken our assumption, which is here, and we've transformed it into the thing that we wanted to prove, which is 3 to the k plus 1 is less than k plus 1 factorial. And so that, in conjunction with our base case, proves that it's true, holds true for all n greater than or equal to 7. So for this statement here. Okay, any questions on that? So every time you do these, the math, the proofs might be a little bit different, but the basic steps, you should always remember the basis step and the inductive step. They always take on basically the same forms. How did we get k plus 1? So just simply by math, we didn't do anything special. We just observed that 3 times k factorial was less than k plus 1 times k factorial. So this right here. This is true because 7 is greater than 3. Well, actually, this should be 8, I suppose. Yeah, this would be at least 8. But regardless, it's true for both 7 and 8. Yep. And then k plus 1 times k factorial is equal to k plus 1 factorial. So yeah, the math, I'm hoping you understand the math, but that is not the most important part of this. Generally speaking, on the proofs that you have to do, we try and keep the math simple, especially on the quizzes. And in these examples, this math would be, more complicated than you would normally see. Okay. Any other questions? Okay, so our next example, we're going to prove something a little more mathier. Did we see summations yet? Maybe we should come back to that one after. Yeah, so I'm going to come back to that one after because it uses sigma notation, which we're going to learn in this lesson coming up. So I'll do this example, and then after the first set of lessons, I'll come back to that other example, and we can work through that. Okay, so now we're going to prove 2 non-parallel lines in the plane intersect in a single point. Actually, we know that that's true. So 2 lines in the plane. So lines, mathematically speaking, go on forever. If you say line segments, then we mean a line, something shorter than an infinite line. But when we talk about lines in the plane, we generally mean infinite lines. But if you can think of it as line segments as well. This proof works if you consider line segments. So these 2 intersect in a single point right here. So we're going to prove that for n lines, there are at most n times n plus 1 over 2 intersections. So if I put a whole bunch of lines here, I will have at most, if I have n lines, I'll have at most this many intersections. So each intersection, so we can count them 1, 2, 3, 4, 5, 6, 7, and so on and so on. So hopefully the problem itself is clear. So our base case, we would say for n equal to 2 lines. So that has one intersection, and that is less than n times n plus 1 is, so n is equal to 2, so that's 2 times 3 over 2. So we're using this formula here. And this is equal to 3. So yes, one intersection is less than 3, so it holds for the base case. Okay. So now our inductive hypothesis, we're going to show, actually, so I'm going to break it down a little bit differently here for k lines. There are at most k times k plus 1 over 2. Again, that's using this formula. And this is our inductive hypothesis. So this is what we hypothesize to be true. And then so the inductive step is we're going to show for k plus 1 lines, there are at most k plus 1 times k plus 2 over 2 intersections. So I broke down the terminology a little bit here. You don't have to do that. So before we were always combining our inductive hypothesis and inductive step, and you can continue to do that. I just wanted to break it down a little bit to show exactly what we're saying in each of these instances. So our inductive hypothesis is the thing that we're assuming to be true. In general, this would be P of k. And the inductive step is to show that our inductive hypothesis implies the next step in our induction. All right. Okay. So our assumption is k lines have at most k times k plus 1 over 2 intersections. So again, this is a little less formal than we normally do when we have the math, because we're going to actually describe things a little more here. So this is our assumption. Sorry, my pen seems to be, there we go. I think one of my buttons is sticking. So assumption. So now we're just going to sort of, in this case, we're just going to describe what happened. So if we add another line, it will intersect each other line at most once. So it intersects the k existing lines at most once each, since these are straight lines. So it adds at most k additional crossings. So then we have 3. So we have k plus 1 lines have at most, by our inductive hypothesis, we have the k existing lines have this many crossings plus another k crossings for the line that we added. So then we can show that, actually, instead of rewriting that, we'll just continue it here. So this is k plus 1 over 2 plus k over 2, or 2k over 2, right? So we want to get the common denominator so we can add them together. So this is less than or equal to k, and again, k plus 1 plus 2k over 2. And this is less than or equal to k plus 1 plus 2k plus 1 over 2, right? Since we just substituted k plus 1 for the k here. And then, oh, my pen is really not cooperating. And then, so we have 2k plus 1 plus k plus 1, so that's actually equal to k plus 2, k plus 1 over 2, which is, in a sense, what we wanted to show, right? So therefore, we can conclude that k plus 1 lines have at most k plus 1 times k, or sorry, k plus 1, k plus 2 over 2 intersections. Okay, so then that's it. This is basically the definition of what we wanted to show. Okay, any questions? Okay, good. So then our final example we'll come back to later. So let's get on with the rest of the lecture. So let's go to sequences, series, and sums. Again, these are based on slides by Dr. Robert Collier, and I've modified them, so if you find any mistakes, they are almost certainly mine. Okay, so last week we talked about introduction to induction. And induction is basically how to prove something for all entities. And weak induction is like this. So p to the k implies p to the k plus 1, plus the basis step, of course. Whereas strong induction, we can take all of the previous values before k plus 1, and we can use them to prove k plus 1. And it's important to note that weak and strong induction are the same thing. There's really no difference. Just weak induction hides some details and is easier to work with, and it's often sufficient. So we don't really need to use strong induction. So this week, induction examples, we already did that. We're going to look at sequences and sums. So we're going to look at arithmetic and geometric sequences and sums. We're going to look at closed forms. So closed forms are really just a way of expressing these sequences and sums so that they're easy to compute or calculate. We're going to look at sigma notation and sigma notation operations. So this is just a way to express sums. And then we're going to go to introduction to set theory. So we're going to look at set operators, Venn diagrams, and Cartesian product. So set operators, these are just a set of operators that turn our sets into propositions or other sets. But we'll see that. And then if there's time, we're going to get into set operations and identities. So we're going to look at membership tables, equivalent expressions, and set identities. And you're going to recognize a lot of this from propositional logic. it's very, very similar to it. So let's put similar. So a lot of that's going to be familiar, and it's going to possibly feel like review. Okay. So introduction to sequences. So a sequence is an ordered arrangement of elements. So what does that mean? Ordered means basically we can give them, we can assign them each a number, so 0, 1, 2, etc., and then they exist in that order. So that's what a sequence is, and this is the set of integers, and so z plus is positive integers, and z star is the same thing but starting at 0. So we frequently use these types of short forms. So we use, so a lowercase letter and a subscript is used to denote an item or term associated with n. So we map, so the nth item, we could express it as a to the subscript n when we're dealing with general sequences. So that's, of course, it's a variable. So for instance, if we had a sequence, a subscript n is equal to n to the -2, so n to the -2 is equal to 1 over n squared. Those are the, sorry, -2. So we can denote a sequence using these curly braces and this variable a with a subscript n. That's just one way to denote it. So you might see that mostly you're going to see them in sigma notation, but this is a viable way to do it. So then if we wrote this, this is actually equal to this sequence up to, up to an, or, up to a infinity, essentially. So in this case, 1 over n squared would be equal to 1 over 1 squared is 1, of course. 1 over 2 squared is 1/4. 1 over 3 squared is 1/9, etc., etc. Okay, so that's what a sequence is. Is there any questions on what a sequence is? It should be fairly straightforward. Just basically an ordered arrangement of things. But we're going to look at two main types of sequences that we can actually evaluate and do operations on. So we're going to look at geometric sequences, and we're going to look at arithmetic sequences. So this is common factor, or maybe not common factor. Well, actually, we'll just go into the official description. Common difference? No. So it is a fact. It's not a common factor though. It's each successive term in the sequence is expressed as a factor of the previous, right? So a geometric sequence has the form a times ar, or ar squared, ar cubed, up to arn. So where a is the initial term and r is a common ratio. Yeah, no, we're starting with geometric. Yeah, you're right. For arithmetic, it would be the common difference. So r is the common ratio. So that means when I talk about two successive terms in my sequence, they are separated by a factor of r, right? So to get from ar squared to ar cubed, I had to multiply by r, and so on and so forth. So these are typically defined for z star, yeah. So 0, 1, 2, etc. Okay, so let's look at some of these geometric sequences and see how we would define them. So a is the initial term and r is the factor. So in this case, a would be equal to what? Or maybe we'll do the first one and then we'll get you guys in on the second one. So a Yeah, a is equal to 1. So the initial term is 1. So the initial term is sort of easy. Yeah, and r is equal to 5. Right, so we multiply by 5 each time, so yeah. Good. All right, what about this one? So we have a is equal to what and r is equal to what? A little more complicated, but so a is, of course, fairly straightforward. Yeah, 1 and 1 over square root 2. Perfect. Good. So this is a little bit trickier, I guess, because I haven't expressed it as a fraction, although, so the first term is, of course, fairly easy. So a is equal to 3. Since we're defining it over, starting with 0, so r to the 0 is just 1, so the first term is, generally speaking, a. R is equal to, yeah, 3/4, yes. So r is equal to 3/4. Right, good. What about here? A is equal to, well, -1, of course, but what's r? Yeah, so they're both -1 in this case. So all of these are valid geometric sequences. So an arithmetic sequence has the form a plus d, a plus 2d, a plus 3d, up to a plus nd. So we're no longer dealing with these geometric sequences with the factors. Now we're dealing with a being the initial term still, but d is the common difference. So the difference between the previous term and the next term is d. We just add d to it. And these sequences are typically defined for 0 through whatever, again. So these are pretty straightforward, but it's worth it to go through just to make sure everybody's on the same page. So what would be, so this should be d here. So what would be the a and d of the following sequences? So a in this case is equal to -1, and then what's our d? Yeah, 4, perfect. This is pretty straightforward stuff. So a is what and d is, yeah, high school review. Yeah, but it's still worth it to make sure it's sometimes easy to get lost in the notation, even though these concepts are simple, right? So it's worth going over. And in this case, we start with 7, and the common difference is, of course, -3. So we can subtract as well, although technically we're adding a negative term. Or, well, yeah, that's generally how we look at it anyway. Good. Any questions on geometric or arithmetic sequences? All right. So a series of the expression is the expression where all elements in the sequence are operands for summation. So what that means is I'm going to take whatever my terms are, and I'm just going to add them all together. Well, I'm not going to sum them right away, but so the series means before summing them, I'm expressing it as an addition. All right, so this series is 1 plus 1/4 plus 1/9 plus et cetera, et cetera. And then the sum of this is the evaluation of the series. So I want some answer as to what this is equal to, and that's going to be my sum. All right, so we can evaluate these pretty easily. So in this case, 1 plus 3 is 4, plus 5 is 9, plus 7 is 16. 1 plus 2 plus 3 is 6, plus 4 is 10, plus 5 is 15. Now it's not quite as easy, right? I could go through all of these numbers and add them up, but that's actually getting to be quite difficult and tedious. And then here I go off to infinity. So what does that equal to? Or is it equal to something sensible? So these are the sort of the questions that we want to try and answer. So these cases are not so easy, but we want to have some sort of answer for them anyway. So what we want is called a closed form. So if you look up closed form, it's called an expression with finite operands, but we sort of abuse that notation. We, loosely speaking, just use it as to mean a simpler form, since an expression with finite operands, well, this is an expression with finite operands, but it's still not very pleasant to work with. So when we say closed form, we mean something easier to work with, generally speaking. Informally, that's what we mean. So how would we find a closed form? So, well, that's what we're going to do. So first, we're going to find the closed form for an arithmetic series. So what we're going to do is just express it in general terms. We're going to use some algebra, and then hopefully at the end, we come up with something that's easier to work with. So this is the way we express an arithmetic sequence. So a plus d plus a plus 2d. Sorry, this is an arithmetic series, not a sequence, all the way up to a plus n minus 1 times d. So this is the series associate an arithmetic series expressed in general terms. So let's let b equal this, which is the final term in the series. So that's this one here. And then, so what we're going to do is we're going to try and express it a little more simply. So this is the same expression as up here, but we've just substituted this b in for all this stuff. So we got a plus d plus a plus 2d, all the way up to b minus 2d plus b minus d plus b. So b being the last term in this series. Okay, so is that clear what we're doing there? Any questions? All right. So since addition is commutative, we can reorder the terms. So this is our original term, original series, and written in the original order, and then we're going to write it again backwards. All right, so this is just in reverse order, so b plus b minus d plus b minus 2d, all the way back to a. And one thing you might notice, so we're going to shrink it a little bit and stretch it out. And then we're going to add these two terms together. So we get 2 times the series is equal to, so this is a plus b for these two terms here. And then you'll notice we have a plus d here and a minus d here. So this just, those two things cancel each other out, and we end up with a plus b there. We go on to the next term, we have plus 2d here and minus 2d here. So again, this is going to look like a plus b. And in fact, every single term in the series is going to cancel out the common difference. And so we end up with a plus b plus a plus b. So let's a second to erase that here. Good, clear, any questions? All right, so now we have n of these terms. So we can express that much more simply. So 2 times the series itself is equal to, or the sum, 2 times the sum is equal to n times the first term in this series plus the last term in the series, where n is the number of terms in the series. Okay, so then we can, through the magic of algebra, we know that our sum is equal to n times the first term of the series plus the last term of the series divided by 2. And yeah, this is just the same thing. These little animations don't show up so good when you print them as PDFs. So I'm just repeating myself here. All right, so now we have this nice closed form expression. So this is actually a closed form of an arithmetic sum. And we can recall that b is equal to this, and we could substitute back in for b. Of course, that gets a little bit ugly. So now we have this expression, but the nice thing about it is we don't have to, we can express it in terms of the initial term and the common difference instead of looking at what the last term would be equal to. Okay, any questions? Good. All right, so how would we prove that the sum of the first n natural numbers is n times n plus 1 over 2? So this is essentially 1 plus 2 plus 3 plus up to n. So we can use our closed form formulas. So we know this one. We know b is equal to n and a is equal to 1. So if we substitute in for those, we get n times 1 plus n over 2, or n times n plus 1 over 2. So we can show that this sum, we've proven that the sum of the first n natural numbers is this closed form using our using the closed form that we developed. We can also use the initial term and the common difference. So if we substitute this in for our b, so now we have a is equal to 1 and d is equal to 1. So we get this, and if we cancel out this 1 and this 1, then we get this n times n plus 1 over 2 again. So using our two different closed forms, we get this nice simple closed form for a very common series, which is which is 1 plus 2 plus 3 plus n. So we see that one quite often, which is why we want a nice closed form for it. There's also another way to show that this is true, and this is a little bit of an aside, but it's something, I guess, an interesting piece of math history. So who was it? Gauss, I believe, that figured this out. His teacher gave him this, told them to sum up the numbers between 1 and 100 as an exercise, thinking that it would take a long time to do, and then this famous mathematician, I believe it was Gauss, figured out a faster way to do it by basically coming up with this closed form. And how he did it is he drew this picture where, so this is, if we count the number of blocks, we have 1 here, and then we have 2 here, 3 here, 4 here, 5 here. So if we want to add all of these up, one way to do it, since we don't know how many, we don't have any easy way to count these number of blocks, but if we say took a copy of all these blocks, painted it a weird color green, flipped it 180 degrees, and then lined it back up. So technically this should have the grid on it, et cetera, et cetera. But if we did that, then we've doubled the number of blocks, and now we have a nice rectangle. So we can easily count the number of blocks in this rectangle. Use a formula for the area of a trapezoid. Top has length 1, bottom length and height. Yeah, that would work too. Yeah, so yeah, you can use that as well. They're a triangle, and you can use that as well. Base times height over 2. So the dimension of this rectangle are n here, and then we've added 1 to the length of the rectangle. So then so we have n times n plus 1 is the number of blocks, and then since we've doubled the steps are half of this area, then we're going to divide by 2. Okay, so that's just sort of an interesting little piece of math lore. You'll probably hear it again and again. But yeah, any questions on this part? All right. So now we can use this closed form, which is you know, quite often we have to add up all the numbers in some from 1 to whatever. So here we could say 1 plus 2 plus 3 plus 4 plus 5 is equal to 15. Or we can try and use our formula, which is 5 times 5 plus 1 over 2, which again is 15. So it's much easier. 5 plus 6 plus 7 plus 8 equals 26. Or we can use this n times a plus b over 2. Now you'll notice our n in this case is 4, since there are 4 terms. Our a is 5, and our b is 8. So 4 times 5 plus 8 over 2, which is 13 times 4 divided by 2, which is 26. All right, good questions. It's all pretty easy, I guess. All right, so now a geometric series we can express like this. So a being the initial term and r being the ratio. So if r is less than, or if r is between -1 and 1, then we say the series converges. So what that means is that as the series gets larger, the sum approaches some constant value. So it'll never be bigger than some number, and we can actually figure that number out. But here's a couple ways of visualizing that. So if we have r equal to 1/2 and a equal to 1, then we have this series here. So we have 1 plus 1/2 plus 1/4 plus 1/8. And this sum converges to 2 as n approaches infinity. And so there's one way to look at it is this. Here's the series, and we have these 2 blocks. Each block represents 1. So the first one is this block. Now we want to add 1/2 to that, so we can add 1/2. Now we want to add 1/4 to that, so we add 1/4. Now we want to add 1/8 to that, so we add 1/8. Now 1/16 to that, add 1/16, and we can keep going. 1 over 32, 1 over 64, and you'll see that we never actually fill it up unless this series goes to infinity, in which case we say at the limit it's equal to 2, right? So that's sort of a geometric way of looking at it to sort of get, and this is what happens in general for all of these converging geometric series. So there's another example here. If we took r equal to 1/4, so we have 1 plus 1/4 plus 1/16 plus 1/64. So we have 1, so now we have our triangle representing one whole object or whatever. And then 1/4 of it is actually, if we split it into 4 equilateral triangles, then 1/4 of it could be expressed this way. And then we want to add a 16th now. So to add a 16th, we're going to take 1/4 of this one. So we're going to take a triangle that looks like this, and then we're going to put it up here. We're just going to flip it and position it here. And then, so every time we want to add a successively smaller term, we can keep on doing that, and forever and ever. And then you'll notice that if we take this triangle and we cut off this bottom part, well, this bottom part here is actually, the blue represents 1/3 of the total area. And then at each time we can cut off another part of it, and this blue represents 1/3 of the total area. So if this extends to infinity, then the total is going to be 1 plus 1/3, right? So we have our 1 here plus 1/3, so 1 and 1/3. Okay, any questions on that? And you can draw these pictures for any r less than, or generally speaking, less than 1, but you know, technically we can have negatives in there as well, and it'll still converge. All right, so geometric series, if r is less than -1 or r is greater than 1, then the series diverges. So what that means is that as n approaches infinity, the absolute sum gets larger and larger and larger. Can we use stuff from calculus 2 for infinite series? I'm not sure. Calculus 2 was a long time ago. Infinite. Oh, do you want to integrate it and stuff? I would prefer you didn't. Yeah, I would prefer you didn't use integrals or anything like that. If you want to use calculus to confirm your work, absolutely. When you submit work for this class, please do it the way that we did it, just so that we're all on the same page, and then you know, we keep the TA's life easier and my life easier. But yeah, definitely, if you want to use those as sanity tests and confirm your work, absolutely, you should. I would encourage that. But okay, so a geometric series with r equal to 2 and a equal to 1, we would get this 1 plus 2 to the 1 plus 2 to the 2. So 1 plus 2 plus 4 plus 8 plus 16. So if we only did these 5 terms, it would sum to 31. But as the number of terms approaches infinity, the sum is going to approach infinity as well. All right, if we have r equal to 1, of course, then the series diverges as well, because as n approaches infinity, the absolute sum gets larger. So for r equal to 1 and the initial term equal to 2, we have 2 plus 2 plus 2. And as n approaches infinity, the sum approaches infinity. This should be fairly straightforward. And if we have r equal to -1, then the series diverges as well, or it's a type of diverges, because the series actually oscillates between 2 different values. So if we have r equal to -1 and a equal to 2, we get 2 minus 2 plus 2 minus 2. So if we have an odd number of terms, we would get 2 in this case. And if we have an even number of terms, we would get 0. And each successive term that we add would just simply jump between those 2 numbers. Generally speaking, we're not going to see so much of those. You'll see mostly, you know, converging series or diverging series is very straightforward. But this is good stuff to know. Okay, questions on that? So diverging and converging geometric series. All right, so now we're going to find the closed form for this geometric series. So we're going to take the first n terms. So that's, this is the sum, the initial term, and then add each successive term multiplied by the ratio. And then what we're going to do is we're going to multiply the sum by the ratio again. So what that does is, if you recall our, you maybe recall our triangles. We had something like this. So we're going to multiply by r, which sort of shrinks our triangle down to this next ratio, but essentially the same structure is all there. It's just smaller, right? So we're going to take this sum and we're going to make it, in the case of a converging series, we're going to make it smaller. If it's diverging, it'll be larger, of course. But if we multiply every term in our sum by r, then we have ar plus ar squared plus ar cubed, all the way up to arn. So now we have this, our original sum, and our sum multiplied by our factor. So now we're going to subtract these 2 things. So our original sum looks like this, and the new sum with the common factor looks like this. And we're going to write it so that we line up all of these terms that are similar. So we have ar here and ar here, ar squared, up to ar n minus 1 to the n minus 1, and a times r to the n minus 1 here. We're going to subtract these 2 terms. And then it's not too difficult to see that, well, we get a here, these cancel out, these cancel out, these cancel out, and we get minus ARN here, right? So now we have something a simpler way to express it, but we're not quite done yet. So here we can take out the common factor of our sum. So we multiply that now times 1 minus r. And on the other side, we could take out the common factor of a. And then again, we can use, we can just bring this, divide both sides by 1 minus r, or, you know, I like to think of it as just swinging it over and dividing instead of multiplying, but that's just, technically we're multiplying both sides times 1 minus r. So now we have this nice closed form for our sum of a geometric series. It's not quite as nice because we have this exponential term here, but it certainly works. And as n approaches infinity, if it's a converging series, then this term approaches 0, right? If r is less than 1, as n approaches infinity, this becomes 0, and then this entire thing becomes this a over 1 minus r, something very, very simple. Okay, good. Any questions? So we essentially have two different forms of our geometric series closed form. We have this. This is if it's not converging or it's not approaching infinity, n is not approaching infinity. But if it is converging and n is approaching infinity, then we have this nice simpler version. So we can recalculate the series that we did before. So this 1 plus 1/2 plus 1/4 plus 1/8, et cetera, et cetera. So that's, since we're assuming that n is approaching infinity and it is a converging series, we can express it like this. So 1 over 1 minus 1/2, and that's simply 2. So that's sort of a nice, easy way to express it now. The other one we looked at with the triangles, whereas r is equal to 1/4. So this is 1 plus 1/4 plus 1/16 plus 1/64. And that's equal to, if we take the same formula, it's over 1 over 1 minus 1/4, which is 1 over 3/4. And that's 4/3, which is equal to 1 1/3. And that's the same answer that we got when we looked at it visually using our these geometric shapes. Good. Any questions? How are we doing now? We're still good for time. Okay. So now we're going to go into sigma notation. So we've looked at closed form. Now we're going to kind of step backwards. So we can use, this is called this is a sigma. I believe it's, I don't know, is it Greek? Possibly Greek. So if we want to write this series, we can express it using this sigma notation instead of this long drawn out thing with the ellipses. All right, and of course the closed form is n times n plus 1 over 2. So in general, we could express it as we use the sigma and some variable I, it's like the counter. If you've done programming at this point, it's basically the same as a for loop, are very similar. So we have this counter I that takes on each value between a and b, and then it simply adds up each expression that we have here. And these are just, I wouldn't pay too much attention to the numbering. These can be any expression, and they can use values from our sigma. We'll see some examples. So a is the lower limit, b is the upper limit, and I is the index, similar to a for loop. Okay. Questions? All right. So we can take a sigma notation and translate to closed form expressions. However, yeah, this is one good example of it. So this is the closed form that we determined before, where we had a as the first term. B is the final term, and N is the number of items. But sums written using sigma notation, we can manipulate them, often easier than a closed form. So for instance, we can change the upper and lower limit of a series. So these two series are equivalent. So if we have A, or I equals A to B, summed up, and I equals A plus X to B plus X, but we subtract X here, then those are the same. So in this case, we have A equal to 6 and B equal to 10. So we have 6 plus 7 plus 8 plus 9 plus 10. And if we add 5 to the A and 5 to B and subtract 5 in the term, we get 11 minus 5, 12 minus 5, and we end up with the same thing. Okay, so that's one way we can manipulate it, and sometimes that makes a difference between something very complicated and something actually quite simple. We can split a series into two sums, right? Since this is basically just addition, we can take some value C that's between the lower limit and the upper limit, and then we can split it, the sum from A to C, and then the sum from C plus 1 to B. And then those two things would be equal. So for instance, if the lower limit was 1 and the upper limit was 10, we can divide that into I equals 1 to 5 of our expression, plus I equals 6 to 10 of our expression. So it's fairly straightforward. We could split a sum into a difference of sums. Right, so if we have a lower limit of A and an upper limit of B, we can say, well, the lower limit is now 1, our upper limit is B, and we subtract all the ones that we weren't supposed to count, right? So from 1 to A minus 1. For instance, I equals 5 to 10 is the same as saying we take the sum of I from 1 to 10 and subtract the sum of I from 1 to 4, right? This is just, yeah. Questions? Am I losing anybody, or it's all still pretty simple? We can factor a sum. So if I have some common factor on all my items, I can take that common factor out. So here 2 is some constant, and now I can take that constant out because, for instance, if I equals 1 to 3, I get 2 plus 4 plus 6. Whereas if I take that common factor out, then I get 2 times 1 plus 2 plus 3, which if I, reevaluate it and multiply 2 times each term, I can get back to my original expression. All right, so any constant that occurs in that summation, in that sigma notation, we can sort of take out as a common factor. We can split a sum over addition. So this is a little bit different, where we now we have an addition in our expression. So we can split it into two different sums, and that should be, I think, fairly straightforward. Ideally, we would have brackets here. So then this sum of I equals 1 to 5 of I is exactly like integral rules. Oh yeah, probably. It has been a while since I've taken that calculus course. And of course, we could do the same thing if this was a minus sign here. We can nest sums. Okay, so this is the one that most people have trouble with. So everything else is pretty straightforward up till now. Some people have trouble with this. So what this is actually equal to is this I here is actually a constant. It's a constant factor. Even though it changes over here, every time we loop through this side, this I has one single value. So this is sort of equivalent to this. If I take the sum from I equals 1 to A, I times this sum here. All right, so let's Yeah, and then we could break it down as 1 plus 2 plus whatever up to b. So this is sort of equivalent. We will go through some examples of these. So hopefully you can see more of them and get used to them. But yeah, that's all on summations. I just have some examples after this. Let's see, we can take a break now, or we can jump straight into the examples. What would you guys prefer? Continue. All right, that sounds good. Okay. Let me then go to, shouldn't take too long anyway, here. All right. So summation examples. So we're going to start very simply, almost, tediously simple, but it'll help maybe illustrate a couple pitfalls. So this should be easy. I equals 1 to 10 of 1. This is 1 plus 1 plus 1 plus 10 times, right? So that's fairly straightforward. That's equal to 10. Nothing, no big deal there. Here we have I equals 1 to 10 times 2. So we have 2 plus 2 plus 2. Again, that's 10 times, and that's equal to 20, of course. And in general, we have I equals 1 to n, some constant factor here. We can write this as 2 plus 2 plus 2 n times, or 2 times n in this case, or whatever constant we have there. When we go from 1 to some upper limit, we're just multiplying that constant times the upper limit. And in general, these ones where you see expressed from 1 to some value are probably the closed form that you're going to work with, or probably the summation that you'll work with most often, because a lot of other summations can be converted into these, and then they're sort of simple to remember and simple to evaluate. I equals 1 to 10 of I, so that's, of course, 1 plus 2 plus 3 plus 10, right? And that's equal to, who remembers the closed form for that? 55, yes. It is 55, but what's the, how do we express that in a closed form? What's the general form? Do you guys remember? Yep. So it's n times n plus 1 over 2. So that's 10 times 11 over 2, which is equal to 55. And again, this is sort of the most common form that you're going to see. All right. So let's look at something a little more complicated. So what are the sum of the numbers from 1 to 100 that are divisible by 3? Well, I was supposed to erase this, but here it is. So I equals 1 to 33. So here's what we have to factor 3 out. Yeah. So we basically want to take, so we want the numbers from 1 to 100 that are divisible by 3, so we can factor 3 out. So you can write it like this, or you can write it like this. The important part is to realize that, or to make sure that your upper and lower limits are appropriate. So in this case, I equals, when I is at its smallest, it's multiplied by 3, it's 3 plus, and then the upper limit is I is equal to 33 times 3 plus 99. So the sum of the numbers from 1 to 100 that are divisible by 3, that would be them. So we've chosen the appropriate lower limit and upper limit in this case. And yeah, we simply multiply by 3 in order to get that. So then this is equal to, if we use the closed form, so we can take the 3 out, I equals 1 to 33, I, so that's n, again, n times n plus 1 over 2 times 3. So this is 3 times 33 times 34 over 2. And what did I get? 1683. So that's probably correct, unless I made a mistake when I punched it in the calculator, but. All right, so I showed a few extra steps here that you, generally speaking, don't have to show. You can go straight to this part, but yeah. Is that clear, or is there any questions on how we did that, how we figured that out? Okay. What about the sum of all the numbers from 10 to 100 inclusive that are not divisible by 4? I didn't give it away this time. That's good. So how would we express this using our sigma notation? Any ideas? Yeah, same thing, but split versus via subtraction. Yeah, so essentially we want, so we can start with the first part. So the sum of all the numbers from 10 to 100 is should be fairly straightforward since it's inclusive. These are inclusive, so when we say I equals 10, it starts at 10 and it ends at 100. So that's something to watch out for. Okay. And that's I. So that's the sum of all the numbers from 10 to 100. And now we want the ones that are not divisible by 4. So again, we're going to factor 4 out. So we want j equals, and we'll have 4 times j. But from what and to what? So what should j start at and what should j end at? Three to 25, yeah. So 3 times 4 is 12. So that is the first number divisible by 3. So 3 times, if I put j is equal to 2, then the first term would be 8, and that would be below 10, which would not be enough. So j equal to 3 gives us 12 for our first term. So that's good. And then j equal to 25. That takes us right to 100. So 4 times 25 is 100. Good. So then we can evaluate these. And there's a couple different ways to evaluate them. One is to split over, so we can split over, we can take I equals 1 to 100, I minus, yeah, I equals 1 to 9, I. Right, so that's equivalent to this term. And then we could subtract j equals 1 to 25, 4j minus j equals 1 to 2, 4j. And that's, in a sense, sometimes the easiest way to break it down is to break it down right into the, so that our initial term is always 1. And then we have that nice, I guess, sort of easy closed form. So then, all right, let's see if we have 100 times 101 over 2, that's this term here, minus 9 times 10 over 2, minus, and now we have 25 times 26 over 2 times 4. That's for this term. And then this is minus here and a minus here, so we're going to add this term. 2 times 3 over 2 times 4. So the 4 is the constant. Okay, and then once we have that, you can sort of evaluate. So 550 minus 45 minus 1300 plus 12. Yeah, MS Word has a, yeah, I mean, its sigma notation is as easy as any of its other notations, generally speaking. You choose it out of a list and then you fill in the little squares. Or you can use, you know, MS Word also understands LaTeX. So if you, what is it? It's sum I equals 1. And then this is, so these are curly braces. This is the, whatever you call that, the little hat to n. So this will give you the summation. That's the LaTeX version. That'll give you this. And you can use that in Word as well. Yeah, and this is equal to 3717, I believe. Okay, there's of course another way to do it. So we have this other closed form here where we know the bottom term, the lower term, and the upper term. So now we just need the number of terms. So this is equal to all right, so n is equal to, well, what is n equal to? How many terms are there in this first part of the expression? So we're going from 10 to 100. Yeah, 91. So it's actually, it's the b minus a. In general, it's b minus a plus 1 because we're including this first term. So in general, that's how we would express it. And that's, so b is 100 minus a, which is 10, plus 1, which is 91. And then times a plus b, which is, sorry, a plus b is just 100 plus 10. And all of this is over 2. And then over here we have 4 times, again, 25 minus 3 plus 1 times 25 plus 3, all over 2. And yeah, somebody can check my math, I suppose, but this should be something like this, minus 4 times 23, 28 over 2. And that should give us the same 3717 as before. So you can use this, and it does make sort of simpler expressions. Be very careful with how many terms, right? It's a little more complicated. This way is longer, but it's in a sense, you always use this same closed form of I equals 1 to n plus 1 over 2. So it becomes simpler to do, although it's a little bit longer and more drawn out. Okay. Any questions on any of that? All right, so we have a couple more examples to go, and then it'll be a late break tonight, but we're almost there. So here's the nested one what we were talking about earlier. Let's see, where is that? So this is a very simple example, but here we go. But this I mean, you have to think of it as this sigma is sort of nested within this other sigma. So every time this loops once, every time this one loops once, this one's going to loop 3 times. But we can break it down using the same rules that we've already applied. So this is I equals 1 to 4 I, and then j equals 1 to 3 of j, and that's equal to I equals 1 to 4 of I, and then the closed form for this is simply 3 times 4 over 2. Yeah, sorry, I thought I had a constant in there, but I don't. So that's equal to 1 to 4 times I times 6. And then we can evaluate this, this sigma. So we can take out the 6 as a common factor. I equals 1 to 4 of I, and that is 6 times 4 times 5 over 2, which is equal to 60. Okay, so that's a little example of how we deal with that nested version. All right, questions on that one? Okay. So if you go to the Discrete Math Study Center, there's a bunch of other closed forms that are listed, and I've copied them down here, albeit far messier. So sometimes we're not summing all the numbers from 1 to n, we're summing all the numbers from 1 to n squared. So then we have this closed form, which we're not going to prove, but you can use it without proof. That's no problem. If we have I cubed, we use this. Here we have the sum from 0 to infinity of x to the I. Recall that's simply a geometric series, right? So as long as the absolute value of x is less than 1, we can use these. We can use this expression, and this is just a over 1 minus r that we established earlier. All right. Again, I'm not spending a lot of time on these. We've already sort of done this one. I just want to show you them, and then I want you to realize that they're available. Just look them up, and you can apply them. And here's another one. If we I times x to the I minus 1 is equal to this closed form, and yeah, off the top of my head, I'm not sure how they got there. But okay. So then if we wanted so now if we had this sort of nested form, so now we have j equals 1 to I of j, and it's nested in this sigma notation here. So now the upper limit of this sigma changes every time that this one loops. All right, so this gets slightly more complicated. So if we want I equals 1 to 10, and now we're going to give the closed form of this sigma, which is going to be I plus 1 over 2. And so now if we break that down, we have this I equals 1 to 10 of I squared plus I. So now we have something a little more complicated. So now we need these extra closed forms. And in particular, we need this one to deal with the I squared. So we can break it down over the addition. So that is equal to 1/2. So now this I squared plus I equals 1 to 10 of I. So now we have closed forms for both of these expressions. So that's 1/2, and that is 10 times 10 plus 1 times 2 times 10, which is our n, plus 1 over 6. So that's this guy. And this is simply 10 times 11 over 2 for this guy. And so if you evaluate it, I think it comes out to 220, unless I did the math wrong. But yeah, so you can, just by plugging in these closed forms and you know, intelligently breaking down your sigma notation, you can get to somewhere where you can evaluate these expressions. Okay, any questions? All right then. So we'll take a break. These are all the examples I have for today. In the future, if you guys want more examples, just let me know. They're easy enough to come up with. But yeah, and this should give you enough so that you can do the tutorial, and then yeah. A LaTeX plugin for MS Word. I believe if you put insert, so you can do insert insert equation, and then you can just write LaTeX in there if you want. So that will actually work. So when you write, as long as you write it correctly, once you press the space bar, it'll convert it into, yeah, it is pretty neat actually. I'm really glad that they added that. It makes, I don't really like going through the menu every time to look for something that I know how to type out in 1 second. So, but yeah, they added that, so it's nice. Okay. Alrighty. So it's 7:02. We'll come back at 7:12. Yeah, and we'll look at sets. Okay. So before we move on, is there any questions on anything we've covered up till now? Okay. All right, let's move on to set theory. All right. So once again, these slides are largely done by Robert Collier, and the things I've added to them have all the mistakes you find are mine. And all right. So a set is a collection of entities. So we were talking about sequences earlier. So a sequence could be thought of as a sort of a collection, but a set is a more general collection, I guess. So it's a collection of entities. The elements or members of the set are entities that are said to belong to the collection. Everybody can hear me, right? All right, perfect. Okay. So we can have a set of, say, students in the class. We can have a set of positive integers, the set of moves and rock, paper, scissors. So we can define just about any entity we like and include that in a set. So small sets can be written as comma-separated lists in curly braces. So for instance, rock, paper, scissors could be written like this. And then it's these curly braces indicate a set, and that has sets have certain properties. With larger sets, we can use ellipses if the pattern is clear. So we still use the braces, but if we wanted to say the numbers from 1 to 10 are in a set, then we can write 1, 2, 3, dot, 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 9, 10, and that's fine, as long as it's clear. So the number of unique elements in a set is the cardinality of the set. So for a set S that's equal to the numbers from 1 to 5, we say the cardinality is 5, and we write the cardinality like this, using the sort of the absolute value sign. But this means the number of items in that set. So some commonly used sets. So this funny looking R is the set of real numbers. N is the set of natural numbers. Z is the set of integers. Q is a set of rational numbers, and so on. And we can define our own sets as well, but those are some commonly used ones. Some sets can have infinite numbers of members. In fact, all of these sets are infinite. So they're kind of more difficult to express. And also, in general, sets can have complex membership criteria. So our braces or brackets are not sufficient to represent these types of sets. So we can actually specify them using predicates. So something that we learned earlier is going to come in handy. So the set of students at a university, we could say, well, X and X is a student at the university, right? So this means that X is a variable, and it can take on any value in our universe of discourse. So again, our universe of discourse is something that we should be defining when we talk about these set builder notation using the predicates in them. So we take X takes on every value within the universe of discourse, and if this predicate evaluates to true, then that particular item is in our set, right? So the set of all even numbers, we could say all X such that X is an even number, or we can say X modulo 2 is 0. Yeah, this is sort of incomplete. So here's some other sets, all the positive numbers. Depending on what our universe of discourse here, if X is in the integers, then this is basically how you would find the natural numbers. We could say all the things that are green. The universe of discourse could be everything in the universe. That's fine. And this is X. X is prime again. X should be the universe of discourse should be the integers. And we can introduce complex predicates as well. So we could say X is divisible by 3 and X is greater than 12. Right? So we can use the logical conjunction here. So a couple interesting things about sets. Duplicates are not permitted, or more accurately, they are ignored and not counted. And you'll see this in programming too. If you implement a set, generally speaking, they don't permit duplicates. So paper, rock, scissors, these two sets are equal because the rock item would only be counted once. Likewise, the ordering of set members is also ignored. So sets are very sort of a general collection. So paper, rock, scissors is the same set as scissors, rock, paper. Those are both identical. So there are collections with more permissive properties. So multi-sets are bags, permit duplicates, and tuples permit duplicates, and the order matters. And we're going to see these later. And we probably won't see too much of multi-sets or bags. They are just basically sets where you can have duplicate items. So a set can be empty. We denote the empty set with this null character or an empty set of brackets. And sets can also contain other sets as members. So this is sort of a, so this set here would be a member of this set, and this empty set is a member of this inner set. But we'll see how these all work out. Sets also have operators. So it's not just, yeah, we're going to do a little bit of math on these things, but it's sort of very closely tied with logic. So, so we have a set inclusion operator. It's an operator with two set operands. So A is a set and B is a set, and we say that A is a subset of B. So this subset or inclusion operator is a proposition, which means that it has a value of true or false. So if I write A is a subset of B, then that's either going to be true if every member of set A is also a member of set B, or rather more accurately, if and only if every member of set A is also a member of set B, and it's going to be false otherwise. Okay, so here's two sets. So we would say that so this set here is a subset of 1, 2, 3 because every member of this set is also in this set. Okay. Again, every member of this set is also a member of this set, so we would use this set inclusion operator, and these would both evaluate to true. However, if we might have these two are members of this set, but the 4 is not, so what we would write, so if we wrote it like this, it would be false, obviously, but we can express it like this. So that means 1, 2, 4 is not a subset of 1, 2, 3. A, B, C, and X, and the predicate is X is in the alphabet. So is this, should this be included or not included? This set includes subset or no? Yeah, so this is a subset. It's just expressed, they're both expressed differently, but they both represent valid sets. Here we have our club, and of course, that is not in the alphabet, so we would express it like this. Yeah, X the variable, not the letter, yes. And here we have, so should this be a subset of, is this set here a subset of this one now? No. Yeah, it's a bit of a trick question because this is actually, this is not the letter A. This is a set that contains the letter A. And a set containing the letter A is not in the alphabet. So it's a very, I guess, maybe a little bit of a fine distinction, but that's the distinction we make when we work with sets. Of course, set inclusion is not commutative. That means if A is a subset of B, it's not necessarily the case that B is a subset of A. So 1, 2, 3 is a subset of 1, 2, 4, but 1, 2, 3, 4, or sorry, 1, 2, 3, 4, and 1, 2, 3, 4 is not a subset of 1, 2, 3. So that should be fairly straightforward, I think. Can this ever happen? What's the yeah, I think one is, so we're going to get into that. One is, so somebody asked, what's the difference between this operator and this operator? Yeah, A is equal to B. So in this case, A is equal to B. Yeah, it's like, it's a little like less than or less than and equal to, right? So this is sort of a stricter version where this is a proper subset. If we, I shouldn't draw a line under it. But this top symbol here is the proper subset symbol, which we get into a little bit later. Yeah. Right. The one with no line. So we could use the no line here, but in this case, this bottom case, we would need these are not proper subsets of each other if this is true, since A is equal to B. Right. Okay. Any other questions? And the equal with 3 lines. The equal with 3 lines is equivalent. This means equivalent. So it's, yeah. And that's sort of how we use it, is when we say one expression is equivalent to another expression. Any other questions? So in this case, you know, A being a subset of B is not equivalent to B being a subset of A. And this is a useful mnemonic. I don't know. I generally don't have trouble remembering which way this goes, but if you do, then you can use this to try and remember. So set membership. So another operator is set membership. So we have an element as the left operand and a set as the right operand, right? So if we say X is an element of the set S, we express it using this sort of this E looking thing, epsilon. And it's a proposition, the same as the subset operator is. That is, it's true if and only if X is a member of the set B. So in this case, 2 is a member of the set 1, 2, 3. That's true, so we would express it like this. And again, if we wanted to, we can express it this way as well, to say that something is not a member of that set. So in this case, the club is a member of this set. In this case, it is not a member of this set. So what is this one? Is this one a member of this set? No. Yeah, it is not. Yeah, simply because this is a set of 3 sets. That the first set containing 1, the second set containing 2, et cetera, et cetera. So it's not a set of numbers. Is this a member? Yeah, again, that's a no. Since this is a set containing 1, and these are actual numbers. What about this one? Yeah. So in this case, this set containing 1 is a member of this set of sets. What about this? You guys remember? So we have our empty set and empty set. Yeah. Yeah, this is a member of that one, right? Since this is equivalent to these inner brackets, so this null set is a member of this set containing an empty set. Okay, questions on any of this? I feel like this is pretty simple. You guys seem to be getting it. Okay, Venn diagrams. So maybe you've seen or heard of them. So their Venn diagrams are rather simple diagrams that we can use for visual representations of sets. And they are simple, and they are sort of limited because of how simple they are, but they can also be quite useful. So the universe of discourse is shown as symbols. So we write down symbols on some, wherever we happen to be expressing our Venn diagrams. And we use closed curves, typically circles, that are used to indicate the sets. And elements within the circles or the curves are members of those particular sets. Okay, so this is an example of a Venn diagram. So the universe of discourse is all of these symbols plus everything in here and in here. So we have this set, S is X. X is in the alphabet, so X is a variable. It's not, again, it's not the letter X. It's a variable that contains these letters. And this is a set as well. But one thing we should take note of, ABC is not a member of S. So this set, ABC here, is not a member of this set. They just happen to be two sets that are sharing some elements. And in fact, you can't really express sets containing sets using Venn diagrams. So you can't express this using a Venn diagram, at least not the way that we use them. You could, of course, define your own type of Venn diagram, but in this class, we won't be expressing anything like this. So if you see something like this, this is not a subset. This is its own separate set. Right. So here's a possible set of Venn diagrams. So we have the universe of discourse. So it's all these elements: hamburger, chicken. Quadrupeds, so everything with four legs, like a rabbit or a table, or a lion, is contained in this set. And everything that's carnivorous, such as this, I'm not sure, is that an eel? And an owl and the lion are contained in this set. And then these things are outside of any sets that we're representing in this case. So this might be another example. So we have some numbers, and so we have our even numbers would be in this green set. Our prime numbers would be in this blue set, and yeah, these other odd numbers that are not prime would be outside of these two sets. And this 2 is shared between, it's a prime number, but it's also an even number. And yeah, here's another example. So if we have the set of Carleton students and the set of Carleton employees, then grad students and TAs would sort of be both students and employees. Okay, good. Any questions? Okay, so another operator, the union of a set A and a set B, so we write it as A union B, is a set containing all the elements in A as well as all the elements in B. So a union has two set operands and the result is also a set. So this is not a proposition in this case, right? So it returns, in a sense, it returns a set. So if we take the even numbers, union the prime numbers, we would take everything in both of these sets. So this would be the result of even numbers, union prime numbers. And here we have 3 more sets, A, B, and C. So if we had A union B, what would be in that? What should I write here? One, 3, 5, 6, 7, 8. Yeah. So 1, 3, 5, 6, 7, 8. That is correct. B union C. I mean, it should be. I think the trick is clear. C is actually a subset of B in this case. So 1, 3, 5, 7 is simply the set B. A union C is 1, 3, 5, 6. 1, 3, 5, 6, 7. Okay. 1, 3, 5, 6, 7. Oh no, I need an 8 there. That's true. All right, so my mistake was on the last page. Good. Okay, questions? Pretty straightforward. Okay, so the union operator is similar to this logic operator OR, right? The logical OR operator. And in fact, we can represent the set A union B using set builder notation and using the OR as a predicate. So A union B takes all the elements X if such that X is a member of A or X is a member of B. So we can express that set using the set builder notation. So yeah, it has similarities to this logical operator. Good. So the intersection of a set A and a set B, so A intersect B, is a set containing all elements belonging to both A and B. So an intersection has two set operands and the result is also a set, right? So again, it's not a proposition, it returns a set. So the even numbers intersect the prime numbers is what? What should we put there? Yeah, 2. Yes, and somebody put the curly braces, and that is actually even more correct because it is a set. So here we have A intersect B. This should be fairly straightforward. Yeah, it's 1. B intersect C. 3, 5, 7. Yep, excellent. And A intersect C is what? Yeah, the empty set. Good. All right. And again, so our intersection operator is similar to the logical AND operator. And we can use the set builder notation to represent it. So A intersect B is all the elements X such that X is a member of A and X is a member of B. So those are two equivalent ways to express that. So here's again useful mnemonics. Perhaps I find this one actually, I use this in my own head if I'm confused, or I did, when I was a student learning this, the union with the U. So union and intersection. So if we have a union, A union B is equal to B union A, that is its commutative. A union B union C, we can shift the brackets around and do them in different order. It's associative. And intersection is the same way. So A intersect B is the same as B intersect A. And it's also associative in that we can do B intersect C first and then intersect A, or A intersect B first and then intersect C. It doesn't matter. Those are equivalent expressions. Okay. So those the union and the intersection are operators that you'll see quite a bit of. Here's the set difference operator. So the difference between a set A and a set B, which we express as A minus B. You might also see it expressed as A backslash B. Is it backslash? I believe it's backslash. But we're mostly going to use this version here, just to stay consistent. But it's a set that contains all the elements of A that are not elements of B. So again, we have two set operands and the result is also a set. So if we take even numbers and subtract the prime numbers, then what are we left with? Yeah, 4, 8, 12. Correct. So we take everything that was in our even numbers and we subtract everything from the prime numbers. But really, I mean, we're going to end up ignoring these ones because these are not members of the even numbers. But this one was one that was shared. All right, so let's try this again. So A subtract B would give us what? Yeah, we'll give us 6, 8. So the 1 is the one that's in common. So we're going to subtract the 1 from the A. And we essentially ignore the rest of these. So B minus C, or B set difference C. Yeah, so that's just going to be a 1. And A minus C. Yep, so they don't have anything in common, so this is still going to be 1, 6, 8. Good. C minus A. 3, 5, 7. Yeah. Again, they have nothing in common, so A minus B a subset of A, true or false? Well, what do we think? It's true, yeah, it's actually true. So if we look at this is a subset of A, so we have B minus C here, this is a subset of B. Because we're not adding anything to the set ever. We're only taking things away from it. So it's going to be a subset. So yeah, that's a good question, actually. A good observation. All right. So again, we can represent this logically by, so the set difference between A and B is all the elements X such that X is a member of A and X is not a member of B. So this is getting a little bit ahead of ourselves because this is going to be one of the set identities that we're going to see, but it's worth seeing here. You can express it using this set builder notation. So the complement of a set, A, denoted A with the A complement, but using the bar, is a set containing every element in the universe that's not in A. All right. So complement is a unary set operator, takes one set operand, and the result is also a set. So if we take all of the not even numbers, well, I'm not going to ask you to write them all out, but you would take everything that's not in this even number circle, right? So this is not the even numbers. We have the universe of discourse is the set of the spades, hearts, diamonds, and clubs. And the set of black suits is spades and clubs. Then the complement of the set of black suits. What's the symbol for the universe set again? Generally speaking, if we can represent the universe set by U. It's a capital U. So this is the universe. Yeah. All right. So yeah, the complement of the set of black suits is, of course, the set of red suits. So if we did complement of black suits, that's equal to the set of red suits. All right, so the set of carnivorous quadrupeds, here's the intersection of carnivorous and quadruped is the lion. The union of the carnivorous and quadrupeds is all of these guys. Set of non-carnivores is everything that's a quadruped but still not a carnivore, and all of these items out here. And the set of non-quadrupedal carnivores. So the lion has 4 legs, so we exclude them, but we take this eel and this owl. All right. That's so those are set operators. Any questions on any of that? All right. So we briefly touched on tuples earlier. So tuples are collections where the order of the elements matters and duplicates are permitted. So here are some examples of tuples. So 1, 1, 2, F, B, C, D, D. You get the idea. So we can have duplicates and we have to consider the order. And we draw tuples using the regular brackets. So now the Cartesian product of a set A and a set B. So we write it as A cross B is a set of all possible tuples, where the first element is a member of the set A, and the second element is a member of the set B. And so the Cartesian product is often applied to construct a Cartesian coordinate plane. So this is one of the applications of it. So for instance, the set of numbers from 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So the set of numbers from 0 to 5, we can represent as this Cartesian coordinate plane. So now when we have a set of coordinates, if we specify 2, 4, the order matters, right? So we're going 2 along the x and then 4 along the y. So it's x first and then y. So the Cartesian product this is often one common application of the Cartesian coordinate plane is one common application of the Cartesian product. So these two tuples are not equivalent. Right. So we take Cartesian product of the values for x and y axis produce all the possible ordered pairs. So the Cartesian product of the numbers from 0 to 5 would be every single possible intersection point here on our grid. All right, so we could represent them all, and there would be, well, what is there, 6 altogether? So it's not quite 6 by 6, is it? 6 by 6 minus 1 or something? Yeah. All right, so Cartesian product, A cross B. So let's do 1, 2, 1, 3, 6, 2, 6, 3, 2, 1, 2, 6, 3, 1, 3, 6. All right, so that's the Cartesian product. And you can see that it kind of explodes all the possible combinations. B times A. Oh, sorry, no, I did that wrong. Yeah, the first one must be from A, yeah. My apologies. So I actually wrote A and B and A cross B and B cross A together. So this is actually 2, 1, 2, 6, 3, 1, and 3, 6. So A cross C is what then? No, so the definition is that we need one element from each set. No, so it's actually just the empty set because we have no elements in C to draw from. Oops. All right. Make sense? Any questions? All right. So then for any set S, so the empty set is a member of the set S, is a subset of set S, sorry. S is a subset of the set S, and the Cartesian product of S times the empty set is the empty set. So how could we prove each of these assertions? All right, so let's prove them. All right. So for all sets S, or for all S such that S is a set, the Cartesian product of S times the empty set is the empty set. So we want to do a proof by contradiction. So let's go through that. So we want to assume the opposite. So our assumption is that S cross the empty set is not, or there exists. Well, let's work our way through that. So we negated that. So we have this universal quantifier here. So we're going to take the negation of that. And if you recall, we swap out the universal quantifier for the existential quantifier, and then we move this negation down to the predicate. Right? So these are two logically equivalent expressions. And this is quantifier negation. And we can also express this not the Cartesian product of S in the empty set. We can express that as there exists an S such that S there is some set where the Cartesian product with the empty set is not the empty set. So this is doing a proof by contradiction. So we assume the opposite of what we wanted to prove. And now we're going to come to hopefully a contradiction. So in this case, we can instantiate some set. Since there exists, we can use this existential instantiation. Okay, so there is some set such that the Cartesian product of S times the empty set is not the empty set. And then so if this is not the empty set, this implies that there exists some tuple AB that's an element of the Cartesian product of S times the empty set. So we're sort of, yeah, I'm playing a little bit loose with the, we are normally very strict when we do these kind of proofs, but I'm kind of, I'm just plugging in the definition here of this, or some, an alternate representation of this, this expression. So now that we have, so we could say there exists a B element of the Cartesian product, and that is modus ponens and 4. 4 and 5 in modus ponens. And then we can again use existential instantiation. So this is just a little bit of review of proofs as we work our way through this. No, this is, I mean, I just sort of, I mean, I plugged this step in without really explaining it first, right? But these are just equivalent expressions. I explained it using English instead of, but if I wanted you to use something like this in an assignment, I would give it to you. I would say, you either have to prove it. Yeah, you would either have to prove this, or I would say you can use this without proof. Okay, so I'm just throwing this in as I'm using this without proof. So this is, yeah, some known fact. Okay, so we've instantiated it. So now we have this other known fact. Sorry, excuse me. So AB is an element of this set if and only if A is an element of S and B is an element of the empty set, right? So this is, again, this is a known fact, or the definition of Cartesian product. Okay, and now I'm going to, I want to skip this step, but I'm not going to. So I'm just going to simplify it a bit though, so I don't have to write it all out because it is kind of tedious. So I can use, this is in a sense P if and only if Q, if I substitute P for this expression and Q for this expression. And so then I can use the implication equivalence, or the biconditional equivalence. And then we can use simplification to get what we want, which is if AB is a member of this set, then A must be a member of S and B must be a member of the empty set. And that is 9 and simplification. So 11. So we have, we know this is a fact, so we can use modus ponens to get this, which is 10, 7, modus ponens. Okay, and then we can again do simplification. So B is an element of the empty set. So that's 11 and simplification. However, by the definition of the empty set, B is not a member. So this is definition of empty set. So then we can combine these. So B is a member of the empty set and B is not a member of the empty set, which is, this is 12, 13 conjunction. And that's false. All right, so that's very, and yes, you can actually explain this a lot simpler. We want you to go through all these steps so that just to make sure that you're logically hitting all the important parts. But in general, as you go further, if you take math courses at the second year and the third year, this would be an awful lot to write for such a simple proof. And you can express it a lot more simply. The problem is when you're first starting out, if I allow you to try and express it more simply, then people just write paragraphs and paragraphs and paragraphs, and you have to try and read through them and see if they've made any sense at all. I mean, some people are very good at it, but other people, and I mean, it's perfectly natural because I did the same thing when I started out. But so yeah, we have this very specific algorithm for proving even these simple things, even though it's a little bit tedious. At least we know that you're hitting all your steps. So, okay, any questions on this? Any parts you need clarified or? Okay. So prove that the empty set is a subset of a set S. You know, for, sorry, my pen malfunctioned. For all S, for all sets. So the fact is that the empty set is a subset of S if and only if for X, a member of the empty set, X is also a member of S. All right. So this is important in this proof. We know this is true by definition. So we do not need to prove it. We want to prove this. So how do we prove this given that one is true? So this is what we're trying to prove. We know that this is true. And this is true if and only if this is true. So what we're going to do is basically prove this part is true, and then if that's true, then that must be true. Does that make sense? All right, so we want to show that X, member of the empty set, implies that X is a member of the set is true. Anyone have an idea of which proof we're going to, or which proof type we're going to use? So let's all right, so let's go. So the first fact in proving this is that contradiction. Yeah, I mean, contradiction is my favorite, but we can do something even simpler here, since the definition of empty set is that X cannot be a member, and this is the definition of empty set. So that means this is our other fact. So let's actually, I'll write it down again. So that means this could be expressed as false, implies X is an element of S, right? Since this is false, because this is true. So again, I'm explaining in English what I'm doing, which it's kind of a little bit bad form, but yeah, false antecedent. Yeah, so this is actually evaluates to true. And this is, it's a vacuous proof or trivial. Or what did you call it? False antecedent. Yeah, that sounds good too. All right, so we've shown that this is true. Since this is true if and only if empty set is a subset of S, then we've shown that empty set is a subset of S. All right, questions? Okay, prove that S is a subset of itself. Again, we're going to use the same style. So S is a subset of itself if and only if for all X, X being a member of S implies that X is a member of S. So yeah, since this is true if and only if this is true, we can prove this. And so we can break this down into cases. So either X is a member of S, or it's not. So, well, Yeah, actually, we can just use universal instantiation. And now either X is a member, and this is true implies true, or X is not a member, and this is false implies false. So this is true or true, and that's true. Yeah, and then you can use universal generalization to say that since we've instantiated some arbitrary element, we can use universal generalization to say for all X, if X is a member of S, then X is a member of S. Okay, any questions? All right, so we've proven those sort of trivial things, but they're good things to keep in mind. So any set S is a subset of itself, and the empty set is a subset of any set. And what was the other thing? Oh yeah, the Cartesian product of S times the empty set is the empty set. Step 2. Yeah, so when I instantiated this X, I don't know anything about it. So I said for all X, so X is, yeah, I guess I didn't really explain that part very well. So X is arbitrary, which means that we don't know if it's actually in the set S or not. So then we're going to break it down by cases. So either it's in the set, and then this is true, and this is true, or it's not in the set, and this is false, and this is false. So yeah, I sort of made a leap here that I didn't really explain very well. It's just because we've instantiated an arbitrary item, yeah, because X can either be in S or not in S, then we have to prove it for both cases, or show it for both cases. But in both cases, it's true. Good. Any other questions? All right. I wonder if we can get through this last set of slides. How you guys feeling? You guys want to do some more? What do we got left? 20 minutes. Maybe I'll wait on that last set of slides. I don't know if I can get through it all, and I'd rather not. I'd rather show it as a complete set of slides. Yeah, I'll post these OneNote examples, and I actually have neater versions of them that I'll post for you. The other thing I can do is I can go back to that induction example if you guys like. Actually, that's what I will do. So this is all the material I'll be presenting for today. I'll go back to that induction example with the sigma notation that I didn't prove earlier and prove that, and then that'll be it for the class. Okay, so yes. Here it is. Okay. Where was that? Okay, so here's using sigma notation, we want to prove this. So if we sum up from I equals 1 to n of 1 over I squared, we want to show that it's less than or equal to 2 minus 1 over n. So again, we have the basis state, the basis step and the inductive hypothesis. So the basis step is we'll take n equal to 1. So 1 over 1 squared is less than or equal to 2 minus 1 over 1. And that is 1 is less than or equal to 1, which is true. So our basis step is true. Now we want the inductive hypothesis. And in general, the inductive hypothesis takes this form. So that means we want to assume that I equals 1 to k, 1 over I squared is less than 2 minus 1 over k. And this is our assumption, our inductive hypothesis, if you will. All right. So what we're going to do then, now we want to sort of turn this P of k into this P of k plus 1. So what we're going to do is we're going to add 1, I equals 1 to k, 1 over I squared plus 1 over k plus 1 squared. And we're going to add that to both sides so that we maintain this inequality. So this is math, add 1 over k plus 1 squared to both sides. All right. Three. So now we're going to do, so we can combine this and this to get I equals 1 to k plus 1, 1 over I squared, right? Hopefully that makes sense. And that's less than or equal to, less than, did I say less? Should be less than or equal to, sorry. Less than or equal to 2 minus 1 over k plus 1 over k plus 1 squared. And our claim is that this is less than or equal to 2 minus 1 over k plus 1. All right, and this is going to be math and a lemma that we're going to show. And so if we follow that, k plus 1, 1 over I squared is less than or equal to 2. And this is the definition of P of k plus 1. So that's what we want, but we still have to show this step in our lemma. All right, and so here is our lemma, lemma 1. 2 minus 1 over k plus 1 over k plus 1 squared is less than or equal to 2 minus 1 over k plus 1. All right, so 2, we're going to say minus 1 over k less than or equal to minus 1 over k plus 1. So that's math. We subtract 2 from both sides. And now we're going to actually do math again. We're going to add 1 over k plus 1 over k plus 1 to both sides. So on this side, we get the 1 over k here cancels with this negative 1 over k, and we get 1 over k plus 1 plus k plus 1 squared is less than or equal to, and this cancels with this, and we're left with the 1 over k here. Okay, Questions? Okay. So now if we multiply everything again, I'm going to put what we're doing before. So we're going to multiply by k plus 1, all the terms. So that means we get 1 plus 1 over k plus 1 less than or equal to k plus 1 over k. And then, so that's 1 plus 1 over k plus 1. Why is this a lemma? All right, I'll finish up and then I'll explain. You use lemmas when, actually, you just use lemmas when it makes the solution more clear. So I could have included all this in the actual proof. It doesn't have to be a lemma. So you're, in a sense, correct there. But it's nice to actually take this complexity and just move it to the side, because the statement of the lemma, this is actually fairly simple and we can apply it. It makes this proof nice and short, right? If we just assume that that's true and then prove it later on. 1 plus 1 over k. And that's true because 1 plus 1 over k plus 1 is less than or equal to 1 over k. It's actually less than, right? So 1/3 is less than 1/2. 1/5 is less than 1/6, or sorry, 1/6 is less than 1/5, et cetera, et cetera. Okay, so that's so the lemma is proven. All right. So that's, any other questions? Okay, that's it for tonight. So that was a bit of a long one. We almost used all the time, but yeah, I'll stick around for another 10 minutes, answer any questions that anyone has. Other than that, that's it.